Welcome everyone. Welcome to today's event on opportunities and challenges for HVDC and power electronics in the UK, and a collaborative event by CIGRE B4 Study Committee and the CIGRE UK NGN. My name is Jianang Li, the communication lead of CIGRE UK NGN, and I'm currently an assistant professor at the University of Birmingham. So some housekeeping. The event will be approximately 1 hour and 10 minutes. So all participants will be muted. Please be aware that the event will be recorded. After the event, once we've got consent from all the speakers, the recording will be sent via email. Please use chat function to ask any questions during the presentation. Q&A sessions will be held at the end of each presentation. For today's agenda, we'll start with a 5-minute introduction to the CIGRE UK NGN and CIGRE B4 Study Committee. We will then have 4 presentations, each for 30 minutes, including question and answers. The first presentation is GB Transmission System Operability Considerations for HVDC and Power Electronic Applications by Dr. Dechao from National Grid ESO. And then HVDC and Power Electronics Technology, Market and Outlook by Dr. Theodor Heath from University of Manchester. We will then have 5 minutes break at 2 p.m. At 2 p.m., we will have the evolution of FACS application in the GB transmission system by Dr. Mark Osborne from National Grid ETO, followed by acoustic noise considerations on HVDC converter stations by Chidinma Agwu from WSP. At 3, we will wrap up and close the event. So let me give a very brief introduction to CIGRE UK NGN. What is Next Generation Network? So basically, NGN is a professional network for engineers studying or in the early stage for their career in the power industry. The UK NGN, we actually have more than 10 years of history. We established in 2007, and it's actually one of the earliest CIGRE young member group across the world. There are quite a few benefits of joining NGN, including free for all students and for the first 3 years of young professionals. Also, we organize events on regular basis. So in the past, we've got quite a few site visits and also young member showcase. And in the past year, because of pandemic, most of our events are held online. And actually, we've done quite a few online webinars with our counterparts in some other countries as well. So if you're interested, please keep an eye on our social network and get in touch. Thank you much. And next, let's welcome Dr. Dechao to give a brief introduction of CIGRE B4 Study Committee and present on the topic of GB Transmission System Operability Consideration for HVDC and PE applications. Dr. Dechao is the elected UK regular member of CIGRE B4 Study Committee since August 2020. He's currently a power system engineer and a subject matter expert in DC system and power electronic in National Grid ESO. Dechao? Ying, you're muted.
So can you see my share screen?
Yes.
Okay. And good afternoon, everyone. And thanks for your time to join this call event by NGN and our CIGRE UK B4 Study Committee. And I'm Dechao from National Grid ESO. As Johnny mentioned, I'm currently the CIGRE UK regular member of the B4 Study Committee on DC systems and power electronics. So first of all, I will give you a very brief introduction of the CIGRE B4 Study Committee. And you can see the scope of work, and B4 is really focused on the state-of-art technologies, including the high voltage direct current system and the power electronics applications installations for AC systems, and we also involve some DC system and equipment and power electronics for some emergent applications. For example, the distribution networks and the power quality improvements. And for some emerging applications like the battery storage, and we consider to include the DC converter for energy storage is also under the umbrella of the B4. And we also have some collaborations with another bodies in CIGRE, for example, the overhead lines, cables, or system performance with another bodies in CIGRE to have the joint working groups as well as some collaboration events as well. And you can see the structure and the leadership and the administration. And Jianang Li from Canada was elected as the chairman of the B4 since 2020 from the Paris session. And there are 4 advisory groups for some different topics. AG01 really focusing on the strategic direction for the B4, and the AG02 and the 03 is for the communication on newsletters and our website. And AG04 is a kind of the share our best practice for HVDC and FACS system performance. And we just established a B4 Engineer 1 to try to involve the more young engineers and the specialists and professionals to join our NGN. We try to hear your voice. So a welcome to all the young members. If you have any interest in our B4 events, just join us. Thank you so much. And in terms of the B4 in the UK, I'm currently the UK regular member, and my colleague Chidinma Agwu is currently the CIGRE UK B4 technical panel secretary, and she will also present today. So maybe you will know her later. And so if you have any ideas or any communications, just feel free to give me and Chidinma a shout. And so far we have 15 ongoing working groups focus on HVDC and power electronic applications, also focus on some emerging applications, new concepts, and asset management and network studies. So after this event, I will share all slides so you can have a detailed look. If you have any interest, just contact us. We have 15 working groups. So this is a brief introduction of the CIGRE B4. And then I will go to my slides for the presentation. And Johnny mentioned I work for National Grid Electricity System Operator, which is responsible for balancing the generation and the demand in GB's electricity system. And I work in the network operability team, so I try to provide some insight into the GB transmission system operability considerations for HVDC and the PE power electronics applications, particularly currently with increasing integration of the HVDC and the power electronics. And my slides have been structured to follow the 3 topics. First one is potential roadmap for HVDC and power electronics, how in support of UK's ambitions net zero targets by 2050. The second one is potential impacts and challenges for GB systems, particularly on system operability with the increasing integration of HVDC and the power electronics applications. The third topic is potential opportunities for HVDC and the power electronics applications to help maintain and or enhance GB transmission system operability. And I will also highlight some ongoing collaborative activities across the UK and wider to co-address challenges or co-explore opportunities for HVDC and power electronics in the UK and wider. After my presentation will for 20 to 25 minutes, and then I will arrange 5 to 10 minutes question and answer session. So if you have any questions, just let me know. Okay, so go to my first topic. I will give you about the roadmap for the from 2020 to 2050 about the HVDC and power electronics applications. As you know, currently the climate change is a global topic for the sustainable development of human being. And in our power industry, the climate change is a really hot topic, and we should, for the UK, there's a common event is the United Nations Climate Change Conference 2021. We call it COP26. It's a really big event for the global power and energy industry, and net zero is currently a really hot topic for all the players in the global power and energy industry. And for our UK government, it has set its ambitious net zero target by 2050. And it's a very exciting news for all the players in this industry. And then how can we expect the future evolutions of the technologies in the coming 13 years since 2020? How can the scenarios for different HVDC and power electronics technologies? So I try to find some clues from my slides here. And for clarification, my slides just touch upon the power electronics applications, only for capacity growth. I know some HVDC and power electronic applications can be used for the network enforcement. I believe the presenter Mark Osborne will expand a bit to and touch more about that topic. So you can see the generation mix in 2020. The thermal power plants powered by fossil fuels still play a very important role for the power generation. And but another indicator that the wind, especially the off-wind, have been a very active contributor to GB's power generation since 2020. And what's the future in the 13 years? Our ESO did a fantastic job, and we provide a future energy scenario to predict the future 13 years power generation in terms of the different technologies based on different scenarios. To meet the 2050 net zero target, and we consider a scenario called a consumer transformation. One is to 2050 net zero target is met with the measures that have a great impact on consumers and is driven by higher levels of the consumer engagement. So, and we also consider another three scenarios like system transformation and leading the way and the steady progressions. So based on different scenarios and conceptions, so you can the evolutions of different technologies for the power generation, and you can see the big picture for the generation mix in different years. So this one is on the right one is consumer transformation, and you can see the another three for different scenarios. But when you see all those four scenarios, maybe you can have a very quick conclusion that you can see the deep green color and the light green color stand for offshore wind and onshore wind. They in the future 20 to 30 years, offshore wind and onshore wind will be the key contributors to GB's power generation in support of UK government's net zero target. And you can see the different other technologies based on PE-based interconnectors, solar PV, as well as other technologies, for example, battery storage will contribute a lot to the net zero target as well. And another conclusion that you can see the roadmap. Another one is significant decline in the thermal power plants, including the large-scale power synchronous generators. Currently, they contribute, is a key players to provide an inertial short circuit level and in support of stability for the electricity system. So, and this could be some features of the GB electricity system. The first one is when I touch upon offshore wind and onshore wind. The one feature is the decarbonization with high integration of the renewables. The second one is the feature where from the centralized thermal power plants to decentralized power generation installations include wind, PV, interconnectors, and another renewable installations and another technology as well. And you can see the other features in the future electricity system will become the power electronics dominant one, with the high penetration of the power electronics installations. And the final one is the significant decline in thermal and power plants. Let's go back to the specific technology. First one, as mentioned, offshore would be really important for the GB system. And currently, we only have the 10.5 gigawatt installations, according to UK government's ambition target by 2030. The target would be the 40 gigawatt installation of the offshore wind. That could be a really challenging task for the GB system. And sorry, it's a typo. It's 2050. According to different scenarios, for example, the customer transformation scenario, by 2050, the power, the capacity will reach up to more than 100 gigawatt. But for the very consecutive forecast, based on the steady progression, there could be 70.7 gigawatt. So it's still very high challenging. And currently, the ESO established a project called the Offshore Coordination Project. It has been set up by the ESO with the support from Ofgem and the Department for Business, Energy and Industrial Strategy to identify the most beneficial approach to develop the offshore networks. And the different approach have been assessed during the phase 1 of this project, and now it's go to the phase 2 of the project. And the outcomes of this offshore coordination project will be an important enabler for delivering the government's 2015 net zero ambitions. And another message from the offshore wind development currently, the HVDC technology can be considered in the UK for the integration of the large-scale offshore wind farms. So the Dogger Bank wind farm project will be first UK HVDC connected offshore wind farm with a power rating of 3.6 gigawatt. Several HVDC links will be installed, constructed and installed for Dogger Bank wind farm area A, B, C respectively for such application. And when we talk about the interconnector, so far currently we have several interconnects to connect GB system with another regions and the countries, and the power rating can reach up to 6 gigawatt. And according to the government's energy white paper, the target by 2030 is 18, and at least 18 gigawatt of interconnector will be installed. And by 2050, according to the leading the way scenario, the target will be 28.2 gigawatt as the ambitious target, but with this consideration as the steady progression, 16.7 gigawatt will be considered. And another feature for HVDC that currently the voltage source converter HVDC technology become the mainstream for the interconnector, because you know, for the two interconnectors in GB, they use the conventional current sourced converter HVDC is for IFAR and BrainNet. And currently, for the VSA HVDC for its application in the UK, the power rating can reach up to 1.4 gigawatt in the UK, and the first such application will be launched as estimated in 2021 this year, is the North Sea link to connect GB system with our neighbor country Norway. And another concept is of the multi-purpose interconnector, because so far all the interconnector has been planned and designed as the point-to-point application. So in support of coordination, offshore coordination and the future NAD applications, maybe the multi-purpose interconnector will be considered to connect as the interconnector as well as the integration of the offshore wind. So this is just a concept. I think some developers have already proposed some ideas about this new technology and concept. Okay, let's go to the onshore wind. It's very straightforward. According to the future energy futures for the future energy scenario, so most future offshore wind, as expected, will be connected to the distribution networks, but still some cases, some growth in transmission level onshore wind, particularly in Scotland. According to the customer transformation, by 2030, the installation will be more than 26.2 gigawatt. By 2050, there could be 44.6 gigawatt. And for the solar, you can see similar to onshore, there could be a very steady enhancement for the solar installation as well. And for the leading the way forecast by 2050, the installation could be reach up to 88.6 gigawatt. And we can consider maybe the new features in our GB system is the emerging applications of the electrical storage, particularly for battery storage. And for the electrical storage, they will consider some battery-based storage as well as the thermal one or other applications and V2G, for example. And but for the battery storage is as relevant to current B4 as relevant works. According to the leading the way forecast, by 2050, there could be 28.3 gigawatt installation of such battery system, and they could reach up to 1418 gigawatt hours for the energy installation. So you can say this could be the significant development for the battery storage as well. And so you can see from those slides, you can see the specific roadmap for different power electronics technologies, including HVDC, onshore, offshore wind, solar, and energy storage. And let's go to the second topic on potential impact for system operability. So, as I mentioned, one feature that with the high integration of the renewables and another power electronic applications, another feature is a significant decline in the portion of the synchronous generators, because currently and in the past, synchronous generators contribute a lot to the inertial and short circuit level, which would be a very important network parameters for the operation of the electricity system in the UK. However, with the declined portion of the synchronous generators, the first impact that it will lead to the decline in the system inertia. As you know, system inertia is a key characteristic of the electricity system that defines how much energy is available in the rotating masses of the machines, including the generators and motors that are directly coupled to the system. Because for all the PE applications based generators, the power converters is kind of the decoupled the generators with the electricity system. In this way, it will lead to the decline the system inertia, and it will trigger the cascaded impacts. First one is because due to the lower inertia, the system need a faster frequency response to balance the system and capture the frequency fall in a low inertial system. And the second one is relevant to the protection of the low frequency demand disconnection scheme, because the RFDD is designed to arrest the frequency fails for extreme system events such as the system splits and prevent a full system collapse. And the demand will be automatically disconnected by RFDD relays when frequency drops below predefined limits to balance the system. However, due to the low inertia, the frequency can drop change faster in such a low inertial system, and will trigger the predefined settings for RFDD stages more quickly than was expected. It will increase the risk of tripping extensive demand, which may result in an over-frequency event after this initial low-frequency event. And finally, as inertia declines, it will trigger another cascaded effect. For example, it probably will have some impact on other parameters like short circuit level. In this way, this will provide adverse impact to lead to the further instability for the whole electricity system. So the impact of the low inertia due to the high penetration of the power electronic applications should be carefully considered. The second one is about short circuit levels. As I mentioned, another impact is it will trigger the decline the short circuit level with the high integration of the power electronics and the declined portion of the synchronous generators. As you know, first one is network protection are designed to detect and safely isolate faulty equipment as quickly as possible, leading the fault effects on the wider system. Protection systems are designed to have a very high degree reliability, but depends on the short circuit level being high enough to trigger a protection relay. It means that if you don't have a high short circuit level, it will potentially trigger the mal-operation or no operation of the protection transmission protection. So National Grid ESO have been worked closely with other TOs to understand the impact of the decline as a short circuit level on protection system. And some case studies have identified that for some big car protection, for the transmission system, including the overcurrent and earth fault protection, there could be some risk under in specific regions. Another one is called the phase-locked loop converter. So currently, most PE applications are based on the grid following technology. PAR is a really important tool to measure the system voltage to provide a reference for the control and operation of this PAR-based converter. So it means that the decline in total circuit level means that the PAR converter may not keep reference with the system during a fault period. And this poses a risk that for the operation and operation of the grid following converter, particularly during your fault, and maybe it will lead to more adverse impact on the system operation during and after fault for the electricity system. And considering those potential risks and some current, I will give you the current development in National Grid ESO and wider, and consider any opportunities for the HVDC and power electronics to address those impacts and challenges. And first of all, National Grid ESO have set up a program called the Stability Pathfinder, with aims to specify products and service as required for maintaining the system stability, considering the inertial short circuit levels and other network parameters, and which we try to find the most cost-effective way to address those stability issues. And we have different phases. Phase one focused on the stability service, and phase one has been successfully delivered. In January 2020, ESO awarded contracts for securing 12.5 GVA seconds of inertia for the period until the end of March 2026. And currently, the phase two is ongoing, and it is focusing on the increasing short circuit level around 8,400 MVA in Scotland, where it's a challenge for the high penetration of the renewables and power electronics. And currently is at the stage of the launch connection review. And for the phase three is ongoing as well, is focusing on the increasing inertia as well as the short circuit levels in England and Wales. And it's just kicked off at the very initial stage, and so far it's at the stage of the launch the pre-tender information.
Sorry, there's 2 minutes left, please.
Okay, thank you. And another consideration is the first one is how can we use some external resource to provide to enhance the inertia and the short circuit level. Another one is how can we explore the opportunities from the converter-based generators, for example, HVDC, wind, PV, and battery. So we explore think the grid forming would be a very promising technology from the power electronics applications, including to provide inertial short circuit level to improve and maintain stability, and to explore its functionality for another network support. And for National Grid ESO, and we just published a system operability framework document to dig out to provide a high-level review of this technology. And we established the Grid Code Modification Working Group 167 to provide the guidance and the legal requirements provided to understand and suggest the non-mandatory minimal specification required for provision of the GB grid forming. The currently is at the stage of the grid forming best practice group is ongoing, and we try to provide guidance for the implementation of the grid forming technologies for the future customers and stakeholders based on our grid code modification. And for the another examples, the NSOE launched a very good report as the guidance for the grid forming for the high penetration of the power electronics interface the power sources. And in our CIGRE working group is ongoing is CIGRE B4.184. According to the scope of work, one session or part of the work we are focusing on the grid forming in support of the HVDC applications. Okay, thank you. That's all my slides, and thanks for your time. And if you have any questions, so you can let me know. Thank you so much.
Right, thank you much, Dechao. And actually, we've got quite a few questions. So because of time, I think let's answer one of them, and then the rest of them, if you could type them into the chat. So we've got a question from Ying. So Dechao, the UK has experienced record electricity prices in the recent weeks. Strong gas prices have fed through to the power market. There are also some wind curtailment due to inclement weather. How do you see the expected 18 gigawatt interconnectors by 2030 can affect the market? Thank you.
Because yesterday I went to the Ofgem website, and Jianang, can you repeat part of the question?
Yeah, sure. So basically, the electricity price has been a lot more expensive in recent weeks, and considering this very strong gas price to the market, so what do you see the expected 18 gigawatt interconnector by 2030 can affect the market?
First of all, I'm not an expert in the electricity market, but you know, I'm not so sure about that, but I know the functionality of the interconnector, because you know the interconnector, the functionality and trading is based on the price. If the in the European electricity market, and currently is the net import of the electricity from those interconnectors, and in the future, if we have the extensive renewable energies, we can use those interconnectors to export the renewables to the European market. But I'm not so sure how can this will influence on the price due to the gas price.
No problem. Thank you much for your answer. And for the rest of them, could you probably type them into the chat to answer them? Thank you. So okay. Next, let's welcome Dr. Theodor Heath for his talk on HVDC and power electronics, technology, market, and outlook. Theodor is now a teaching-focused lecturer in power energy at University of Manchester. I think you're muted.
Yeah, thank you very much. Just getting my system set up. I'm hoping you can catch my share here.
Yes.
Fantastic. And I'm hoping you can hear me now loud and clear as well. Thank you very much for having me. You've already seen this slide. Welcome to the opportunities and challenges for HVDC and power electronics in the UK event. I'm just going to go straight into it because I know we're tight for time. So, as I've already been introduced, my name is Theodor Heath. I'm a lecturer in the Department of Electrical and Electronic Engineering at the University of Manchester. I completed my PhD in modular multi-level converters for HVDC under an iCase sponsorship, which was actually sponsored by National Grid, and Dechao was in fact my industrial contact at the grid after Paul Coventry retired. After finishing my research, I worked for GE Grid Solutions as a power electronics engineer in the R&D valves department, working on the next generation of modular multi-level converters, and since January this year, I've been back at the university. I'm hoping to give more of an overview of the technology, market, and future outlook, rather than a deep technical review, which ties in quite nicely to Dechao's presentation anyway, but I hope you'll find it interesting and helpful. So to kick off, let's take a look at the global outlook for some relevant markets, namely in grid infrastructure, renewables development as a whole, and more specifically wind and PV, which we know to be a big future market for HVDC and power electronics, especially in the UK. So huge investment is needed between now and 2050 to enable this desire for renewables heavy generation. And that's estimated at around $14 trillion by Bloomberg, just on the power system side. And in addition to this, there is a predicted $15 trillion of investment expected in power capacity development, 80% of which is expected to be in renewable generation and batteries. Now, all of this money is to drive forward technology and increasing renewable generation adoption towards an estimated 55% of electricity demand being met by wind and PV globally, but more locally, somewhere close to 70 to 80%, which is obviously pretty ambitious. This is taking into consideration patterns of EV adoption, electric vehicles, and electrification of heat. And of course, we have to take into consideration that any global estimates are bound to be wildly inaccurate. However, more than anything, I think the scale of the investment here and the sheer figures is a clear indication of the challenge, but also the opportunities ahead. So if we shift from the global picture to the UK market for HVDC and facts, the most recent estimates I could find put the market size at approximately $8.5 billion in the UK, with a predicted compound annual growth rate of 7.4%. So we're looking at 13 billion or so by 2026. Now, this growth rate, again, is quite heavily influenced by external factors, such as government legislation and tariffs. But in my opinion, for us to meet the targets, these really ambitious targets that Dechao has already been through, set out by the UK government, especially in the more ambitious future energy scenarios from the national grid, considering things like green electrolysis for hydrogen, electrification of heat, and wide usage and adoption of electric vehicles, this market is presently undervalued. We can see that the market for wind projects is booming, and it's pushing the pricing on contracts for difference 20% below the expected auction prices, down to just above £40 per megawatt hour. And predictions push this below £40 per megawatt hour over the next decade, and that can be compared against an average lifetime cost of £90 per megawatt hour for a combined cycle gas turbine. But as has already been raised, that is a little bit out of date, perhaps, in the most recent energy market, given that wholesale energy prices have risen to a monthly average above £100 per megawatt hour in 2021. Spot prices hitting approximately £2,500 per megawatt hour as well, thanks to this huge surge in natural gas pricing and these wind speeds, low wind speeds, which are on average across the UK. So we'll have to see what happens with these markets once the gas markets stabilise, I suppose. So in the previous slide, I'd mentioned UK targets. Well, if we look at the UK's National Energy and Climate Plan for 2020 and the National Grid Future Energy Scenarios that Dechao has been through for 2021, we can see that the total final energy consumption target to be met by renewables is 29%. So that's just under double our present level. And in order to meet this, we're looking at putting 40 gigawatts, or meeting a target of 40 gigawatts of offshore wind, up from a 10 or so that we have at the moment. This is all likely to need to be connected in some way to the grid, and in the most recent cases, because of the complexity and the distance away from shore, we've been using VSC HVDC to do so. The plots that are being released by the Crown Estate are looking to be increasingly challenging and further out, so it's likely that VSC HVDC is likely to be take a bigger picture in the future. In addition to this, again, as Dechao's kind of mentioned, there are 13 gigawatts of new interconnectors planned, reinforcing links with Ireland, France, Belgium and the Netherlands, and connecting Germany, Denmark and Norway as new connections. We also have kind of intra-connectors within our own country, the Eastern Link and the Western Link, for example, using HVDC to reinforce our own grid. And many of the most recent wind farm projects have already been decided. So you can find more information about VSC HVDC if you're interested from Professor Mike Barnes's VSC HVDC newsletter, which if you're not receiving can be really helpful, so get in touch if you don't get that. Just a gentle plug. So why is the market so big for HVDC? Well, it's because there's lots of applications. For connecting wind farms, building interconnectors, and in some cases, even considering changing pre-existing AC networks into DC networks for capacity expansion. But we can achieve that in some cases with the use of fax devices to increase the capability. So we have to consider these kind of projects on a cost effectiveness basis. In the UK, these inter-region HVDC links that I mentioned, Western Link between Hunterston and Connors Quay, or Eastern Link between Peterhead and Drax, are more likely than the conversion of AC networks to DC networks for strengthening the transmission network. There are a number of technical documentation on all of these examples, such as the ones I've referenced here, two of which came from this working group, the B455 HVDC connection of offshore wind power plants, or B460, which is designing HVDC grids for optimal reliability and availability performance. And then B241 looked at the conversion of AC lines to DC operation. We're also learning a lot from demonstrations in China in multi-terminal HVDC, including the Nanao Sushan projects. Moving on then to a brief review of the technology readiness levels from a multi-terminal grid perspective. And this has been assessed by the promotion project, CIGRE itself, and ENSOE, with the most ready technologies at TRL 9. So that's the kind of actual system in proven operational environments, being the monopole and bipole voltage source converter topologies, especially with half-bridge submodule design, which we've seen lots of. Less so for full bridges down at TRL 8, just because the application for these is a little bit more niche. But this is all perhaps unsurprising because we've seen these applied to a number of projects in the UK and globally. Across both of the submodule topologies, there are always ways to improve, including cost, reliability, and I'll touch a little bit on power density in the next slide. Then we can look at HVDC circuit breakers, and there's a range given for these because there's different types at the moment. TRL 6 for the voltage assisted resonance converter, or VARC HVDC circuit breaker, TRL 7 for the hybrid HVDC circuit breaker, and TRL 6 for the active current injection circuit breaker. And it says up to TRL 8 because we think we're going to be learning some lessons from the Zhangbei 4-terminal HVDC link, which is live testing these advanced HVDC circuit breaker prototypes at the moment. We'll drop then further a little bit down to TRL 6 for meshed grid control, multi-terminal grid control, which is in active research in both industry and academia. And we drop even lower still again to TRL 4 for DC to DC converters for HVDC. And that's mainly due to the complexity and cost of these systems. The latter two, mesh grid control and DC to DC converters, they're the key areas for weakness at the moment in this path to an HVDC supergrid, whatever form that may take, but not necessarily limiting us from achieving multi-terminal HVDC grids in general, as long as they've been planned around appropriate voltage levels. So I mentioned some areas for improvement in submodules for VSC HVDC converters. One of them is always in power density. So while VSC HVDC is a fantastic groundbreaking technology, it's still limited in power transfer capability in comparison to LCC. So it still offers much higher power levels. LCC, as we saw in the most recent record-breaking link, the 12 gigawatt link in China between Changji and Guquan, but to push up the power capability in VSC without significantly increasing the complexity and size of the system, unsurprisingly, we're going to need to drive forward the core power electronics. So here I've considered some leading IGBT manufacturers and their high power IGBT packages since around the early 2000s, which have pushed from power levels of about 4.1 megawatts in early designs up to 6.5 megawatts in more recent designs. And this is all in the same sized package, which is why I talk about power density. I've put an asterisk against the 6.5 megawatt value at 6.5 kV because these are very recent switches. They're still quite a modern advancement in the technology. And as the technology matures, it's possible that we'll see something like 1200 amp modules coming out at 6.5 kV, pushing the power capacity to 7.8 megawatts. Publications as of May this year are already talking about this development, so I think this is likely to happen. As of my last check, Dynex and Infineon are not yet offering a 1000 amp 6.5 kV IGBT, but if they're not, I'm sure they are soon, so we can keep an eye out for that and the way that's going to change the market on the side. After this, then what's next? Voltages we would like to keep going up, I suppose, to maintain our efficiency, low current. But this is only one method. But are we reaching the limits now of what silicon can offer us within this package size? Or perhaps IGBTs themselves as a design have taken us as far as possible and we can look at alternatives. So maybe we are looking at silicon carbide, gallium arsenide, different switch constructions such as integrated gate commutated thyristors, IGCTs instead of IGBTs. But I'm going to leave that up to the fabulous R&D teams to work out. All too complicated and expensive from my end. It's important to note here that all of these advancements in technology will continue to benefit FACTS applications too, but the desire for high power density is kind of less pressing for on-land developments than for offshore platforms where we're really trying to minimize the size. So next, on to the lowest TRL in this multi-terminal grid consideration, which is DC to DC converters. When HVDC systems are designed to work together with matching DC voltage levels, there isn't really a need for DC to DC converters other than for secondary systems for potentially stepping down for consumption at lower voltage levels. However, in the future, if we're looking at this supergrid scenario, we may wish to interface pre-existing 320 plus or minus kV systems to the next generation systems of plus or minus 400 or 500 kV. So we may need to consider this technology as something in our arsenal later on, even if we don't require it right now. But you can see that's why perhaps this is the lowest in the TRL levels at this stage. They will also enable us to interface LCC, line commutated or current source converters, with the voltage source converter schemes, because it helps us to kind of decouple and segment those grids into unique operational areas for protection. An excellent review of the present state of this technology is available in the B476 document, referenced at the bottom of this slide. And in general, at this point in time, there isn't really a significant commercial case for DC to DC converters in HVDC applications. Hence, as I've mentioned, the development's limited. However, as our interest in multi-terminal HVDC grows, so will our interest in these systems. In general, the most achievable and beneficial approach at this stage actually seems to be front-to-front connected modular multi-level converters with an AC transformer in between for stepping up or down the voltage, so DC to AC to DC. But we have to consider the cost and complexity of these systems, especially if we're constructing offshore. I wouldn't want to be paying for that platform. It sounds very big and complicated. And a big question will always be, who's going to pay for it? Who's responsible for it? And who's going to benefit from it? What's the kind of cost benefit for that system? And I don't think we necessarily have a framework at this stage that would facilitate that. So a fair way to go on this technology, but it isn't holding us back from interfacing similar voltage levels in that regard. So I'm actually going to move to a slightly different topic now, but mainly back to our discussions on these ambitious UK targets for offshore wind and photovoltaics. So while saving the planet is a top priority, doing it in a way that helps to keep our power systems stable and secure is also really quite important. One of the big considerations at the moment is in assessing the impact of high levels of non-synchronous generation. So, for example, systems that are grid following, as Dechao has already explained, or grid forming. So the Migrate project has concluded that there is a maximum limit of about 68% of connection generation by means of grid following converters. And the rest then needs to be made up of traditional synchronous generation or converter interface generation using grid forming control. Okay, so that's grid forming enables the set of the frequency, whereas grid following is kind of tracking the frequency of the system. However, it's important to note that the stored energy in a traditional synchronous machine is much higher than in the energy stored in a DC link. So if we want to have grid forming converters, in order to kind of get them to work as we want, they have to be supported with additional storage elements, such as batteries, flywheels, maybe even hydrogen storage, in order to be able to provide what is effectively synthetic inertia. But the other important thing to mention there is that most of our power electronic systems don't have particularly high surge current ratings, if any. So they don't behave in the same way as a traditional synchronous generator would, being able to provide maybe 4 or 5 per unit current the instant that the frequency starts to drop, for example. So there's still going to be differences in this figure, depending on the mixture of traditional synchronous generation and converter interface generation using grid forming. So I think, regardless, we're going to be trying to keep much below this 68% level to be confident in our grid stability. But what might this look like in practice? Actually, we kind of have a bit of a case study to present something like this. The All-Ireland network, comprising the transmission networks of the Republic of Ireland and Northern Ireland, already have significant levels of system non-synchronous penetration, or SNSP for short, and they have a 65% limit at the moment, or that may have just changed to 75%, but they have committed to raising it to 75% and higher. And this SNSP level includes instantaneous variable generation such as wind and PV, and HVDC interconnectors, and that's as a percentage of the system electricity demand at that time. Interestingly, according to the Wind Energy Island, on 12th of February this year, the All-Ireland network broke its record for wind generation, and it hit just under 4.5 gigawatts. And that might not sound like much in the context of the UK, but in terms of the All-Ireland network, that is a very big number, where the typical consumption is about 5.5 gigawatts. So the daily wind power numbers provided by Wind Europe at that time also suggested something like a 76% share from wind energy, which is clearly above the 75% target. But the data might just be from the Republic, not including the Northern Ireland, and all of these limits are island-wide, so there might be a bit of data mess that's kind of happening to not make those numbers completely clear. But regardless of the specific proportion, it's a very significant amount, and the All-Ireland grid did not collapse. So it successfully managed the influx of that non-synchronous generation, and it's obviously providing an interesting event to demonstrate this, the stability of the All-Ireland grid. The way in which they can do that is by making use of something called ramping margin reserves forecasting. And according to the CIGRE group, this is a key enabler in the move 65 to 75% limit. But it's worth mentioning that the All-Ireland network does partially rely on HVDC for that stability, but not as significantly, for example, as Denmark, who have similar levels of wind penetration, in fact more on average, but have more strong interconnectors with the European grid, which is very, very large and stable. And it also provides an interesting case for SNSP studies. Another interesting thing about iGrid in this case is that it's dominated by onshore wind, actually, accounting for just over 99% of the installed wind energy capacity. But this is set to change over the next decade, with offshore wind predicted to account for about 33% by 2029, which will be just over half of the total installed capacity on that grid, handled by onshore and offshore wind. So while VSC HVDC may not be a big player in that market, the lessons learned about these interfacing of power electronics at this level are still incredibly valuable. And it gives us a glimpse into life in low inertia land that we'll consider to be an excellent case study in the UK and other countries. Considering all of this information then, a few key challenges for power electronics integration on a massive scale. First challenge in continued development of grid forming control, which will enable operation up to this 68% limit as suggested by the Migrate team, though again, I think we'll be trying to keep below that. As non-dispatchable generation interface through power electronics, through converter interface generation continues to penetrate at transmission voltage levels, we'll also need to consider more demand-side management techniques for managing the load. So where we're unable to curtail or dispatch generation at the right rate, we will need to have methods to change the load in order to maintain stability of our grid. For multi-terminal systems, we need to see a standardization and regulation of DC networks. And this work is already going on in CIGRE, NSOE, National Grid, and loads of other organizations globally. And then we need to understand more about the multi-terminal grid control, protection, and operation, which I suppose is actually 3 challenges in one, but I think they feed into one another, really. Multi-terminal grid control, depending on what protection you use and what you're actually using your converters at each end of that grid for. So at the University of Manchester, we're looking at a number of these challenges, namely in grid forming control, stability assessments for high penetrations of converter interface generation, and additional ancillary controls for VSC HVDC systems. We also have ongoing research in smart load regulation, demand profiling, demand side management techniques, And on future networks, we're also looking at hydrogen networks, storage, grid-level battery storage for frequency response or synthetic inertia in grid-forming systems. Now, I have to point out this is a mere selection, and there are many other avenues beyond this work being carried out by my colleagues and our students that will impact our understanding of HVDC and power electronics globally. So if you're interested in knowing more, then please do get in contact. I think that's everything of my whirlwind presentation that I have for you this afternoon. I hope you found it interesting. There probably is time for a couple of questions. I think I'm in good time. But if you have anything that you want to follow up with afterwards, please do get in contact with me by email or through LinkedIn. Thank you very much.
Thank you, Theodor. We've got a few questions for you. So where are the Chinese vendor in the market, in the UK market for HVDC? Is the market close to them, or what's stopping them competing with those established players? So this is from Colin Food.
Yeah, it's an interesting question. I think the barriers to entry are a little bit complex at the moment. I'm not sure if I have a good answer for you, really. I think it is likely that there's a bit of a tit for tat thing happening here. I believe that the Chinese vendors will be able to operate here in the future, but there may be challenges with IP in some cases. But I really don't have a strong answer for you, so I'm sorry about that, Ying. So Damien, I think it was.
Okay, thank you. The next question is from Dan. Could there be any insights on potential applications of meshed DC grid and DC-DC converters in the UK?
Oh, sorry, whereabouts was that question?
It's in the Q&A section, actually.
Can you repeat the question for me? Sorry.
Yeah, let me see if I can copy and paste and put it in the chat.
Right.
So there we go. Could there be any insights on potential application of meshed DC grids and DC-DC converters in the UK?
Oh, sure. Yeah. So I mean, we're connecting lots and lots of offshore wind to our grid, and at the same time we're creating interconnects with nations and effectively covering or putting cables across the same space in the sea, but not connecting them together. So at the moment we're doing point-to-point links. We'll run we'll build a wind farm, connect the wind farm directly to the UK, and then we have a connection, say for example, between the UK and Denmark. But there are methods in which that instead of us having to effectively waste power, in a sense, transporting it to the UK grid, and then if we were exporting it directly to Denmark anyway for sale, we'd be just wasting transmission losses on that system. We could interface even if it's just a 3-point link between UK to the wind farm to Denmark, for example, would enable power transfer in that direction. But creating a mesh grid then for, let's say, all of the wind farms on Dogger Bank would enable us to have, I would say, slightly more interesting ways of being able to move the power between us and our.
Okay, thank you. I think we've got 2 more minutes, so maybe try another 2 questions. So this is from Damien Jackman. Do you know if Ireland has experienced stability issues, particular SSO?
I think at the moment, the information that I've been able to find on it has been extremely limited. So they haven't had huge amounts of events where they've been greater than that 68% penetration limit. And I think that some of their ability to maintain stability in that system is because they're able to export some of that power into the UK. At this point, I believe that they have really quite incredible ways of managing rock-off. Are up at somewhere comfortably at like 1 hertz per second of rock-off ability. So they're actually in a really strong position to be able to handle those kind of events where they really are very, very low inertia at that time. I'm unsure if they've had significant stability issues, but it would be interesting to see if I can find more information on it. which is what I'm trying to do at the moment to build up that case study. I'll let you know, Damien. Thank you.
Okay, so maybe one last question. So from Ying, how the interconnectors are providing inertia support in the UK?
I'm not sure. I mean, at this point in time, I don't think our systems, our VSC HVDC connectors that we're planning for the interconnectors necessarily are being equipped with the ability to provide inertial support. So I'm not sure how to answer the question. I'm sorry.
No worries. Thank you. I think there are a few other questions in the chat box and also in the Q&A function. So if you can maybe answer them when you are available in chat, that would be great. So for the rest of the shall we have 5 minutes tea break and we'll get back at 2:10, okay? Okay, everyone, welcome back. And next, let's welcome Dr. Mark Osborne for his talk on the evolution of FACS applications in the GB transmission system. Mark is a chartered engineer and joined National Grid in 1997. He works in electricity transmission in the engineering and asset management sector.
Good afternoon, everybody. Hopefully, is this working? So
it is indeed. If you just go to the full presentation screen.
Okay.
Wonderful.
All right. Thank you very much. So good afternoon, everybody. My name is Mark Osborne. I work for National Grid and I have done so for the last 20-something years. As the biography before just kind of summarised, I've been with CIGRE for quite a long time as well, but primarily in the substations arena, so B3. So this afternoon, I'm going to kind of talk to you about the kind of the utility perspective around flexible AC transmission system applications, so commonly known as FACS. Generally, these typically are power electronic based solutions, and kind of we'll talk a bit specifically about them, but also some of the challenges and some of the features. I shall also introduce kind of the latest member of the family that we've introduced earlier this year, a new type of voltage source converter solution, and then kind of finish up with some of the challenges, or should we say some of the issues that we need to be considering as we go through as we develop our networks to be able to absorb and meet the net zero challenge. So firstly, just some kind of basic numbers and things. Now, I'm talking generally about National Grid's equipment, which is England and Wales, but also a number of technologies also the numbers are bigger because we have the OFTOs who have a number of these assets, and also the onshore TOs up in Scotland have some of this technology as well. So there is a larger population than you can just see on the screen. But typically it's divided up into two kind of areas. What's called shunt compensation, so something that's connected to ground, and that primarily is being used to support the network to manage dynamic voltage control, so that during faults we can hold the volts up or pull them down depending on the oscillation to try and kind of maintain the system in a stable nature so that it can recover safely from a fault. And we have a variety of technologies from the traditional static VAR compensator up to the more kind of more recent StatCom designs, and I'll kind of talk through those in a few slides' time. The other side is a series compensation. This is one of the kind of, I suppose, growing areas, and that is more around power flow control. In particular, how do we flex the flow of power during, well, post-fault, but also during steady state conditions to optimize the capacity we can get across boundaries. I mean, as Dechao's presentation earlier was pointing out, there are some significant challenges in capacity coming up. So the first thing is always to optimize what you've already got, because it generally takes a long time to build anything new. So these aren't the alternative to new power corridors or to HVDC or offshore. These are merely a way of optimizing what we've got with the current network, managing that period until we can actually build new capacity. Okay, so the next few slides are going to be kind of a basic introduction to the kind of technologies, what they do. Just for those of you out there who are not intimately familiar with these applications, but the one that you'll see a lot of in most networks are static VAR compensators. So these are a traditional form of dynamic shunt compensation, which use capacitors and inductors coupled with power electronics to facilitate a response usually during a post-fault condition. And these typically will be using thyristors, and those will switch in blocks of capacitance. And this is generally kind of backed off with a thyristor controlled reactor, which allows for the fine control so that you get a variable amount of VARs injected, whether that is a positive or a negative, depending on the network conditions. One of the things that's typically associated with the static arc compensator are harmonics, and harmonic filters tend to be quite a feature associated with SVCs, particularly since wherever you are connecting something, you need to essentially make the background harmonics no worse than they were. Now, obviously, harmonics are generated by a whole variety of other things, but what we typically aim to do is not to aggravate any existing condition, and filters are essentially the method by which this is done. So wherever we have the typically a thyristor controlled reactor, that's is a key part of the design. And the kind of final point on there, a lot of the SVCs use air-cooled reactors. So it's not just the kind of power system effects we need to be looking at when we use any form of FACS device, but also the environmental, and particularly audible noise, and also magnetic fields. And air-cooled reactors are a producer of both of those. So wherever you are using these, you're going to need to be able to cater for that. And audible noise is a particular issue. I mean, anybody recently who's been having sleepless nights with the window open, amazing how far noise will travel at night. So these can be kind of quite significant design challenges you have to consider. So the static, so moving on from an SVC, essentially the flavor or the favorite technology at the minute for dynamic compensation, shunt compensation, is the static synchronous compensator, or STATCOM for short. This is essentially uses the latest generation of inverter based on voltage source converters, and is typically made up of IGBT modules. The big difference between this and the SVC is that essentially STATCOM can do both the positive and negative injection, so you don't necessarily need a capacitor bank or a reactor bank. Now that is fine providing you want a symmetrical injection, and in a lot of cases that is what people want. But in the case of economics, these systems are still more expensive than maybe the traditional SVC elements. So quite often you tend to see requests for a hybrid design, and that's what we have on our network. So essentially you're looking for something in the order of 100 or so VARs, inductive, but primarily we're also looking for voltage support when you get that big voltage dip after a fault. So in our case, a lot of ours are specified for in the order of about 200 to 225 megavars capacitive injection. So that's very, very expensive as a singular STATCOM solution. So you can supplement it by using thyristor switch capacitors. And in the diagram on the right, this kind of shows our layouts that we've recently or installed in the last couple of years on the south coast to support the voltage stability challenges that we have down there. But what these typically involve are smaller harmonics, which can generally be managed within the in the inverter. So the next asset that we have is a series compensation device. This is primarily in this case, a thyristor controlled series compensator, and it is it's a device that we've had installed now for a few years on the northern circuits up in Hutton. And it's key function is essentially to reduce the impedance on the circuits that flow or essentially the circuits that connect to Scotland, because there are there's kind of a stability restriction across those boundaries, and by using a series compensation on both the north and the south side of that boundary, the Scottish TOs have also installed series compensation on their side, but of a slightly different design. And our units, when we were doing the analysis, we identified that one of the key issues we now need to start catering for is the interaction potentially with other assets. Generally, at SVCs, StatComs, people tend to quite often design in isolation, maybe need to cater for harmonics. But as you start looking at series compensation, you now have to start thinking about everything around it, in particular generators in this case, and subsynchronous oscillations. What you don't want to do is have, under certain conditions, a resonance between the capacitance of these devices and a nearby generation or other sources of active control. So this is why we introduce the kind of thyristor controlled element, and what that does is that works essentially behind the scenes to essentially neutralize any emerging conditions. And what this then does is kind of allow us to, well, hopefully have a relatively long-term solution that can deal with future network changes. But something I will kind of mention a bit later is the detailed system analysis and ongoing system analysis is going to become a key part of ensuring that all of our assets are still fit for purpose as they become 5, 10, 20 years old. So that's the kind of what we had. Now this year we've added the latest form of fax device onto the system, so a static synchronous series compensator, quite a mouthful, but affectionately called the SSSC. And this is again a power flow control application based around voltage source converters. So we're moving again from thyristor to IGBT based technology, and we are now essentially with a purely power electronic asset. It is all the work it is doing is via inverter injection. There's no capacitor, kind of AC capacitors or inductors or anything that are providing additional capability. All this is being done in the power electronic space. And so the next few slides, I'm going to kind of focus on this new technology that we've installed. So it's the technology is called Smart Valve, and it is a brand new kind of technology essentially on the world stage. And what we have installed on the northern circuits essentially is a modular solution based on, essentially in our case, 10 MVA modules, which essentially allow us to inject either a leading or a lagging impedance, and then that can help control the power flows on those circuits, either pre or post fault. Bulk of the requirement is for a post fault condition to avoid overloading circuits, so we can optimize the capacity across an overall boundary. So the technology, as you can see there, is essentially that these are just boxes. If we kind of go back into the previous picture, what I'm showing you here essentially is everything inside this box. And then if you want more of it, you just add boxes in series, essentially. So hence why it's called the modular solution. And what it essentially consists of is a VSC valve, which can either inject leading or lagging bars. That has elements of protection around it. But in parallel with this, and this is the kind of the crux around how these devices look after themselves, is essentially what's called something that's called a fast bypass. and it has a combination of power electronics in terms of silicon control rectifiers to provide very fast actuation, and then using volt vacuum switches, which essentially provide the mechanical and the kind of rating capability, so that we get the high fault currents, the high duties that these will need to see under fault duties, that the power electronics are protected. I think one of the key points to mention here really is that these devices are all about protecting power electronics. There is no transformer that is coupling these to the system. This power electronics is directly in circuit. So the protection in here is all about making sure that the power electronics units themselves are not damaged under onerous fault duty conditions. So that there comes a slight difference here to maybe some of the traditional assets that have been used for power flow control, like quadristor boosters or series reactors, which tend to sit there during the fault and have to take the full whack of fault current or over voltages. Here, this bypass arrangement protects the device during anything that is beyond the rating of the power electronic capability. There's a couple of other kind of key points to note here. This technology is essentially wirelessly controlled. It's autonomously controlled in itself, in that there's control on board the devices, but there is no hard wiring up to the unit. So you remove one of the elements, which is a traditional challenge about the kind of potential difference between control systems that are at ground and those are at system voltage, because these units float at system voltage. So if we kind of look at how an installation typically sits, these installations here show this is setting up system voltage, and then these units are just connected in series. The power supply, again, because there is no connection to ground, we have to manage a power supply challenge, and these are energy harvesting devices. So there must be current flowing within the device in order for it to be able to do key functions like provide cooling, actuate elements. There is an element of energy storage within the device so that it can safely get itself to a safe position, and it can kind of do its basic kind of monitoring functions. But there are some interesting aspects that we need to cater for when we look at designing and installing these type of technologies. The other interesting kind of feature here is there's a lot of cooling associated with these. So that's one of the things that we've had to kind of work on the last year or so to kind of make sure that we get kind of understand the maintenance aspects, and we can understand how to make sure these devices operate reliably and functionally in the networks. Here we're just kind of showing a typical installation. One of the key points to notice is that we talked about having a series, it's essentially a parallel bypass. When we install these, so here are the triple SCs, but in parallel with this, we have a mechanical bypass as well. So within each of these modules, there is the vacuum switch and SCR, as we kind of described before, but also within National Grid, we've decided we want a mechanical bypass so that we can put the circuit back into service if we need to take these out for any reason. So we're also keeping these within the substation because of the wireless aspect of communication, and also if we need to do any maintenance or intervention, we kind of want to be able to kind of do this without minimal impact on the system, so we can take this out and then put the circuit back in play. So that's kind of the smart valve. Some of the key features that kind of came up when we were looking at that, but also all our existing fleet of equipment as well, is when we're looking at designing anything new or we're looking at replacing anything, there's a growing requirement to do even more analysis. You can't just do like for like. There was a time where you could just model something in isolation. Now you need to be very cognizant of everything that sits around it, especially active control systems. Certain parts of our network, basically every node adjacent to some of these applications have either HVDC links, large wind farms, large embedded solar arrays. So there is just a plethora of active control systems that need to be catered for and considered. And that is one of the kind of key points, particularly the dynamic performance of these during faults is one of the is something that definitely needs to be understood and considered when you're specifying them and configuring these solutions, because power electronics fundamentally are control systems that need configuring. A lot of time, traditionally, people are always focused on full load. One of the bigger challenges at the minute is actually focusing on light load conditions, and particularly periods where you're going through a transition from one state to another, and so therefore it's what's the sensitivity of that control system, that asset, to those conditions, and being able to kind of model that and be able to understand what that means in the particular control system specifications that you're looking at, which basically means you've got to spend a lot more time looking at your dynamic model. And the big challenge, I think, here, and we certainly kind of ran into, and I don't think there's a simple solution yet, is managing intellectual property. If you've got 5 or 6 different inverter systems in close proximity, each from a different manufacturer or a different utility or a different owner, people won't immediately share the detailed model of that device. Obviously, the OEMs are very keen and protective over their control systems, and especially if there are any issues. So this whole understanding around how to manage and model control system interaction is going to be one of the key issues that are going to be we need to address as a nation and as an industry over the coming years. And then I think marrying with that essentially is then how do you actually test and commission these systems? It's increasingly difficult these days to actually get access to the system, and you don't get long commissioning windows. More often than not, you're kind of not getting the testing conditions you would want either. It's very difficult to get a heavily loaded network when you're doing commissioning, because the last thing the control room want is a fault that will kind of trip off a lot of capacity. So we are having to think better how we can use real-time hardware in the loop testing, things like this, in order to be able to kind of minimize as much of the stage 2 commissioning work that we necessarily have to do. And then that kind of some of these issues kind of roll over into kind of the asset management side of these devices as well. I mean, pretty much everything I've talked about so far is at the design stage and the front end. All these assets will be on the system for anywhere between kind of 10 to 50 years. And there seems to be an assumption at the minute that whatever you do on day one is what it will do on kind of for the rest of its life. And I think we need to start thinking about what's a reasonable lifetime for these assets, especially if we want, when, as Dechao pointed out, that the degree to which the network is going to change over the coming decades is something that has a lifetime of 40 years. Is it going to be still suitable in 40 years' time? So we need to think about how how we can adapt to these technologies to make sure that they are fit for purpose and doing the best they can when they're on their 10th birthday, their 20th birthday, their 30th birthday. Because a lot of the elements that sit within these devices age. All of these systems have cooling, and cooling systems invariably have mechanical parts to them. Those will age and they will wear. And most of the issues with most power electronics typically is a cooling related. The other one tends to be kind of PCB, printed circuit board, cards, which kind of get a burnout or power supply problem. So you need to replace those. So it's making sure that as these assets get older, there are adequate spares, there are adequate alternatives to make sure we can keep them working. And actually the other big one is who actually maintains these, especially the more modern solutions, which are very complex control systems, heavily embedded in firmware and software. With the recent kind of issues around cyber resilience that are coming to the fore within utilities, the understanding and management of that has become much more to the fore. And let's be honest, most utilities are not going to have the resource to be able to manage firmware and software. It's going to be very much the working with the original developers, the manufacturers, to ensure that any updates, any kind of equipment issues can be addressed to make sure we can keep these things operating for the times that we need. So it doesn't get any easier, and we are under increasing pressure these days to be able to demonstrate that the equipment is working reliably and it's doing what it needs to do. And we're actually seeing more kind of complexity on the networks, and we're also seeing more volatility on the networks, whether that is due to weather or a generation mix. So the nature of these assets are going to start working much more frequently, and we're going to need to make sure that they can we can maintain them such that they can do this. So I think just to kind of finish up, I know there's a few questions flying around. So I mean, power electronics are it's fully kind of are going to appear across every part of our networks, whether that is in generation, in the distribution side as active as an active load, whether that is embedded generation, PV, power electronic motors, variable speed drives, battery energy storage. So this dynamicism of the whole network is increasing, and fact devices are going to be kind of critically affected, but also a critical part of managing these issues. So we certainly believe that there, from a transmission point of view, as well as increasing capacity in terms of new HVDC or maybe even new circuits, optimizing what we can push through our network is definitely going to be the first challenge. So we're going to see more of these rather than less of these in the future. And I think we will see more of the kind of a modular approach to technology, the ability to be able to put a small one in and then build it bigger, or to be able to move it around as the network changes, as we put in new capacity somewhere else. We aren't always going to be able to just add new devices all the time. We're going to need to have a more flexible mobile fleet. But I think the thing behind all of this is going to be the knowledge and understanding that we need to develop. The modeling, the complexity with power systems and the assets that sit in them is becoming more and more of a critical issue. We tend to see kind of fewer people in the industry, but actually it's at a time when we probably need more people. And whether it is that transmission, distribution, in the micro generation arena, all of the issues are very, very common. And so I think industries like, or kind of communities like CIGRE and academia and the utilities and the generators and the service providers in between, I think all need to develop a way to be able to share this knowledge, these understandings, these risks, so that we can make sure that we have the best system available, so that we can ensure we deliver a net zero network, and make sure that we are providing an environment by which the UK can prosper. And hopefully I've outlined some of the ways we might be able to do that. And any questions? Thank you.
Thank you very much, Mark. So considering the time, I think let's try to answer one question at least. So this is from Andy Bremner. Can I ask if National Grid has evaluated life cycle costs for smart valve solution versus a more traditional QB-PST application? I understand that in comparison of QB-PST units, that the OpEx costs for smart valves are significant. Is there a significant difference in CapEx costs for initial procurement between the technologies?
We've certainly done cost benefit analysis when we were looking at it's the timing of investments with a lot of the challenges around this, and the reason why something like a smart valve, in this case, a modular approach, you can put in just the bit you need when you need it. We can build up that volume in time. If we were to try and put in the full lot of the full equivalent of a QB, the cost would have been a lot more. But we wouldn't have the same flexibility or the ability to be able to move it. I mean, basically, once you put a QB in, that's it. It's in for life, and it's in for. I mean, it's a transformer technology, so you're looking at something that's going to be there for 40, 50 years. Whereas, hopefully, at the back end of the presentation, I was kind of pointing out that long-term investments like that become more tricky to justify. What we actually need is the ability to be able to be flexible and move around and relocate and build up on something if we need to. And that's where the modular approach that we get from power electronics starts to help.
Okay, thank you very much, Mark. Next, let's welcome Chidinma Agwu for her talk on acoustic noise considerations on HVDC converter stations. Chidinma is currently a principal engineer within the Interconnectors team at WSP.
Thank you very much for the introduction. Good afternoon, everyone. As said, my name is Chidinma Agwu. I'm a principal engineer at WSP, and I'm also the UK B4 Technical Panel Secretary. So for the presentation I'm giving today, just in terms of what I'm going to be going through, I'm going to do back to basics, just a bit of what a converter station is, just to bring everyone to the same level, because I know some people are experts, but I believe there'll be some people that aren't so aware of what a HVDC converter station is. I'll then touch a bit on what it is that defines the noise limits that converter stations are restricted to. I'll then have a chat about acoustic noise in terms of pre-construction, what the considerations are, and then also post-construction, what the considerations are, and finish up with my summary. And after that, I'll try and make sure there's still some time for some questions and answers. Okay, so what's a HVDC converter station? Very easily, it's a station that's operating at high voltage. Usually, again, depending on the country, it's operating at over 220 kilovolts. So in this country, the UK, it's 400 kV. So it's a station operating at high voltage that converts alternating current to DC current, so direct current, and vice versa. And then based on that, we usually have two types of schemes. You have your transmission scheme, which is usually a point-to-point system, and you have your back-to-back scheme. So with a transmission scheme, which is a point-to-point, at each point, so at each location, you have a converter station. So because it's usually in the case of a transmission scheme, you're usually transmitting power over long distances, over water bodies. You need a link connecting these stations, which is usually your HVDC cable or your overhead transmission line. For a back-to-back scheme, it's just one station because these are usually required or installed in areas where you have unsynchronized AC networks, so you have systems at different frequencies. So for example, one of the HVDC converter stations I was involved in is the Al-Fadili back-to-back converter station, which is owned by GCCIA. And that particular station is connecting the Gulf to Saudi Arabia, and one's at 50 hertz and the other's at 60 hertz. In terms of transmission schemes, for example, it's long distance. So an example of that is Rio Madeira, where you have a lot of power being generated in the north, so in the state of Rondônia. And that's then got a link which at the time was the longest in the world, just over 2,000 kilometers long. So you had an overhead line connecting further south in of Brazil, near Sao Paulo, where there's more need for the power. So the technology that's usually used inside a HVDC converter station. So you'd have heard the terms with my with the earlier presenters, my colleagues, saying LCC or VSC. So at the very basis of this, you have your line commutating converter, which is based on thyristor-based technology. And on the other hand, you've got VSCs, which are your voltage source converters, which are based on IGBTs. So depending on the project location, LCCs and VSCs are still required, although I know in Europe it's VSCs that are the more common technology or more common converter station that you'll hear being spoken about. But LCC is a lot more mature, and as mentioned by Theodor, has a higher power capability. So for example, it's used more in countries such as China, India, Brazil, where you want to transfer a lot more power, while VSC converters are used, for example, a bit more in Europe, where, for example, you want the system to be able to support not the system, but you want your converter station and your link to be able to support the AC network. So those are the technologies that are basically that drive the converters. So an example, this is an example of an LCC HVDC converter station, which also reminds me that I'd wanted to mention something that Mark had mentioned with his presentation. So with your SVCs, for example, you have harmonics that are created, and it's the same with your LCC. With your IGBT technology, with your LCC converter stations, you tend to have the need for AC filters. So because you have harmonics produced on your AC side, you need to be able to take these out. You need to be able to clean this before you transfer your power into your network. With VSCs, the harmonics that are created are a lot lower, so you don't usually need an AC harmonic filter, or they'll be a lot smaller. But so this is, for example, an LCC converter station. This is one of the ones which was mentioned in an earlier presentation. So for instance, this is Western Link, which connects the western side of Scotland to Wales. It's a bipole scheme which can transfer 2,200 megawatts. So that's your one pole on that side. That's your other pole. This area here is all of your harmonic filter. So this is your AC filter, which is going to clean out your harmonics. And this area here is your harmonic filter for that pole. So that's your harmonic filter for the other pole. So straight away, you can see the amount of space that is taken up by harmonic filters. What you then have also, you got your converter hole. In front of it, what you can see are your transformers. I'm going to zoom in a bit because one of the items I'm going to talk about are your fans, your valve cooling fans, which are these items here. So that's an example of your LCC HVDC station, Western Link. And another one, this is an example of a VSC converter station, which is an ELFI, which is an interconnector link between Spain and France. So one of the things that you can see straight away is just the size. So you you can see here you've got your building, which is your converter building. So it's got your IGBT stacks in there. So that's one pole, that's your other. You got your transformers at the base there, but the really massive difference is that with VSC and with this particular project, you do not need your harmonic filters. And so the space that you had, the space requirement that you had for these filters, it's just not the same for a VSC plant, which also means that the equipment that you have is less, and therefore the equipment that are generating noise is a lot less. Which then takes me on perfectly to primary components of a HVDC converter station. So the components for these sorts of stations are, again, it's dependent on your project, on the requirements, but these are the main components that every converter station will have, whether it's a back-to-back scheme or a transmission scheme. You're going to have your converter transformers. They're the noisiest things. Again, depending on the design of the station, you might have one massive three-phase transformer, or a lot of the time, especially with a VSC system, with a VSC station, you have single-phase transformers, so you could have 3 per pole, 6 in total that would be operating. You've got your cooling fans, which work with your converter transformer. You have your reactors, AC, DC, and then as mentioned, you have the AC filters, which are made up of reactors and capacitors. You have your converter cooling fans, which remove or help to remove the heat which is created by your valves or by your converters. So it's valve, or it's referred to as a valve, which is a carryover. But if it's an IGBT, we still refer to it as valves. However, if it's an IGBT, we tend to refer to them as converters or IGBT stacks or modules. So you have your cooling fans, which extract the heat from that. You have your HVAC units, so your heating, ventilation, air conditioning units, which maintain the temperature and the ambience within the building. And then in terms of the components that generate noise, these are the main components outdoors, but because your actual converters are indoors and noisy, they're still assessed when you do your studies. You then have your cooling plant motors, which run this cooling plant system to cool the converters on the inside of the building. So there are usually 2, and that's part of the redundancy, but you'd only have 1 in operation. So these are the primary components, equipment, that are considered in terms of generating actual acoustic audible noise, which contributes to the overall noise that your converter station creates. You might wonder, well, what about circuit breakers and diesel generators? They're noisy. However, you would only really run a diesel generator if there's an issue, at which point most of these other equipment isn't going to be running. So you're never going to get that maximum noise that your that your station creates. And then also with circuit breakers, when they actually operate, it's for a very short amount of time. And so those aren't taken into consideration. What is considered in terms of noise is when your converter station is at its noisiest. No, it's not the most technical term, but that is when it's considered. So when it's operating ideally full power, 24 hours a day, 7 days a week, all year long. And so in terms of what defines the noise limits, so in terms of your converter station operating, what you would like is to just have lots of space to design your equipment to be as efficient as possible and to just let it run. However, there are standards and guidelines. So there isn't technically a standard in the way that you would design, say, a transformer, but you have international guidelines, such as those by the World Health Organization, and they recommend that at nighttime, the noise limit should not be more than 45 dB. And again, this is just a guideline. Depending on the country that you're in, and then even depending on the local authority, local laws, those guidelines for what the noise limit will be. In this country, for example, it's 30 dB. And also what's usually emphasized is that the noise limit that would be experienced is the more stringent one, so at night. So during the day, for example, the World Health Organization's recommended limit is 55, but at nighttime it's 45. So what's usually done is that you look at the more stringent requirement to then design to that. So apart from looking at what the actual local regulations are, it would be dependent on your location. So is your converter station being designed to be in a rural area, in an urban area, or perhaps even in an area that's already built up and lots of industry around, because that then affects what your performance limit will be. So for example, if you are in an area that's like really quiet, there's lots of woodland, you might have a few farms around. That farm would be considered what you'd call a sensitive receptor. So the limit, so basically at nighttime, that farm should, for example, not experience more than 30 dB. That's then setting your performance limit for how much noise your converter station can create, so that a certain distance away, where you have a sensitive receptor, it doesn't exceed that level. But again, it depends on the local, on the area that you're in, and then the local regulations. So in terms of a project requirement, when you're building one of these stations, the country-specific guidelines, so local regulations, where it's actually located, all of that is taken into consideration to say, right, you know, either we set the performance limit to be on the boundary, so that's the perimeter, or are there residences, are there people living nearby, in which case those areas become the sensitive receptors. In some cases, and I know this is the case in Scotland, where the project had to be aware of the wildlife in the area. So it wasn't people that were the issue, but it was the wildlife that meant that they still had to follow, that they still had to be in line with the noise limits, even though there were no people in those areas. So then pre-construction, looking at the acoustic noise or talking about the acoustic noise, what I mean is looking at the design and the planning stage. So what you do is consider your equipment, so you know, your transformers, your cooling plants. What you'd also ideally, if it's possible, be aware of is your background noise, what's already existing. So as Mark mentioned, like nowadays, you can't just think that, yes, you're going to build your own converter station, there's nothing nearby. You have other existing systems which create noise, which add to the background noise. And so ideally, when you are looking at noise, you're assessing what's already existing and what your equipment is going to add to that. So when you're doing that, that's how it feeds in from your project requirements, because you want to transfer, for example, 2,000 megawatts between France and England, and what you need to do that. But while you're doing that, you also need to make sure that you are in line with the planning requirements. And I'm aware, as you probably all are as well, that there are a lot of other environmental restrictions, because we have to be aware of what we're doing. So there are going to be ecological restrictions, but I digress. So in terms of acoustic noise, we have to be aware of the restrictions in terms of planning acoustic noise, but we need to be able to meet the project requirements. So in terms of the design considerations, sorry, I started, jump back and finishing back. So you have your equipment specifications, which is your components. You have your background noise levels, which you consider. And what you then have to do are carry out noise studies to ensure that what you design is going to be compliant with the planning regulations. One thing I do want to mention, because I know I said pre-construction, but in terms of my talk today, I'm just talking about acoustic noise in terms of the converter station when it's operating. So what you have to look at beforehand, design and planning, and then what you have to look at afterwards when it's actually in operation. So when you're building your converter station, there's definitely going to be a lot of noise created, but you have the health, safety, and environmental guidelines and that are followed by the contractors. So to make sure that, again, the surrounding areas, but also that the people that are working on that construction site, that they are safe. But for my talk, it's just about acoustic noise in terms of the converter station when it's in operation. So you know you need to design your converter station. You know how much power you want to transfer. what you would usually do is run a noise study. So for this, you'd have certain types of software. I've used Predictor and SoundPlan, but you've also got CADNA. And these are all software that work in line with the ISO 9613, which is an acoustic standard. So within your noise study, what you would consider is your station layout. So if I just quickly run back. So you have your station layout, your building dimensions, your equipment data. So for example, with this one, you've got your station layout. You consider the type of equipment that you have there, your converter transformers, your buildings, their heights, where these are all laid out. These are bits of information that you consider. You have your sensitive receptors, whether this is going to be the perimeter fence, the boundary, or whether you've actually got residences, farms nearby, where you have to make sure that you do not exceed that noise level. So these are then design considerations that you have to make. So you have your equipment specification, you have your noise study. And what you then have to do is a reiterative process. So you can't just assume that, yes, you have a noise study, you're just going to put in a figure for a quiet converter station and minimal number of filter reactors. You actually have to work with the designers and check, is it possible to get a quieter converter transformer? Is it possible from a civil point of view to potentially change the location of buildings? For example, can you have cooling fans in a different area? So it's a reiterative process where you look at your equipment, you look at your design, you look at your layout, and you work with the designers to see what's possible to then provide a compliance study. So this is just an example from a converter station study that was done in Canada, just to show the sort of information that's obtained and that's run to then put together a noise report. So with this slide, it's an example basically of the type of equipment that you'd get. So you have your cooling fans, your transformers, their fans. It says AC unit, but what it's referring to is the HVAC unit, your valves, your phase and smoothing reactor, so your AC and your DC, and then your converter building. So what they've been provided with are the sound power levels, and then they've also been provided with the different octave bands to show the distribution of sound for each of those items. What they would have then done is put the layout as the station is going to be in the location where the station is planned. So what you can see here at the valve cooling fans, it's a bipole. So you've got one converter building here, the other there, the HVAC units, your transformers there, and then your AC switchyard where it connects into. And then with this image, you can just see how if you move out a bit, they've modeled the site around. So they've taken into consideration the area. So you've got a lot of foliage, but then what you've also got here are houses. So for example, you have all these residences, and these would be considered the sensitive receptors that shouldn't be affected. And finally, this is one way of information being provided as a visual model. So what you can see is the noise that's generated from your converter station, because they've put in all that data. And then with this contour map, it shows how at this stage it's down to 30, at this stage it's down to 35, and this is the closest house. This is a close-up of how much noise is generated when you're closer to the converter station. But so usually these sort of reports or these studies, they would actually provide a breakdown of the different noise levels in different areas, but this is just an easy way to see straight away that you're compliant. So what would then happen is you'd have a noise report to say, yes, we're compliant, all the equipment that we've put together, it's been designed, you should have a compliant station. So then post-construction, you've designed, built, installed, commissioned your converter station, it's now operating at full power. So ideally what you would do is get your noise measurements to show that you've reached or that you've achieved the sound, that you've achieved the noise levels that you set out to. So you have a noise report that confirms this. The worst case scenario though is if those required levels are not met, at that point additional mitigation measures would be required. These can be really expensive, especially retrospectively. And so it could be additional civil works, it could be redesign of equipment. And then the issue with that as well is that you could have loss of revenue. So if you have a 2000 megawatt station, but to ensure that you're going to reduce the noise while the redesign is being done, you might suddenly have to transfer 800 megawatts. So now you're transferring less power, you're losing revenue. The other issue with that is that there'll be contractual implications. So you, first of all, said you'd be compliant to that, so you could get a fine because you've exceeded that level. You could also get fined because you would have trading agreements for how much power you're going to be able to provide and transfer. So it's quite expensive, and it's quite important to get it right and to design this properly first time round. So this is just an example of some attenuation measures. So the two images, that's a transformer bund. So what you can do is design the transformer bunds in a specific way to reduce the vibration of the transformers. Here, similar to what Mark had mentioned, you had the reactors which had the enclosures around them. So here is an example of a reactor with an enclosure around it. Other things that can also be done at design stage is to know that you might need individual capacitor can enclosures. So for example, that is your capacitor, and these are the individual cans. So what you'd have is an enclosure for each one. Other things, if necessary, that could be designed at the very start are walls, transformer housings, and even the landscape can be used to help mitigate, to attenuate the sound. So in summary, in terms of acoustic noise considerations, first of all, you need to identify what the noise limits are and what the sensitive receptors are, whether it's the boundary, whether there's farmhouses. You then need to carry out your detailed studies to achieve a compliant station design. As it's not always perfect, but as much as possible, you want to get your accurate equipment specifications to get that data. Where possible, you want to include background information about other systems that are around. And then finally, you build and prove your noise compliant station. Otherwise, as mentioned before, the work can be really expensive in terms of mitigation. There could be loss of revenue and fines because of trading agreement contractual implications. So I hope this has been not too, I know it's been a bit high level, but I hope it's been informative. And thank you for your time. And I'm happy to take any questions.
Thank you, Chidinma. I've got a question, if I may. So you mentioned that there could be potentially very high penalty if it fails once it's built. But may I ask what sort of accuracy we're talking about? So once you simulate it in the software and potentially evaluated the design, what sort of percentage roughly do you think is going to be accurate?
So I must admit I haven't myself carried out an acoustic noise measurement. However, I do remember and I won't specifically say the name just because project information is usually confidential, but I am aware that there was a project where the limit, and this is very high, I'm aware, but the limit that they had to achieve at the boundary was 70 dBA. And when they actually measured it, I believe it was about 71. But again, because that particular station was quite, it was more relaxed, it was acceptable. So with other stations, if the noise limit is, for instance, said it has to be down to 30 and you go up to 33 dB. Sorry, can I just check? Are you saying, are you asking for confirmation of what the variance is or what is allowed?
Probably the variance.
I would
roughly.
say, just from memory, I would say about 1%, but I would be happy to double check this. And if anybody wants to know for certain, I can get back to them, but I'm happy to double check.
Cool. And the other question, if I may, is so as an example, so I've got an EV charger at home, and occasionally I can hear some very high frequency noise from it at night, especially. I'm not sure whether these kind of things will be also considered for substation. So the substation that you just mentioned.
So I'm not sure about high frequency, but one of the issues that you sometimes have with converter stations, and especially with LCC converter stations is that the transformers, because of the harmonics, so the transformers for converter station, for LCC converter stations, they can be subject to tonality. So what that means is just that one or two, what I'm going to do is just very quickly go back to this. So what can then happen with a transformer? You'd almost have a bit of a pitch, and that's because you might have just one specific octave band where the noise is quite high. So I'm not sure about smaller electrical items, but definitely with the converter stations, having that specific pitch at just within one band or within a very narrow spectrum is an issue that's then referred to as tonality.
I see. Thank you much, Chidinma, for your presentation.
Mm-hmm. Are there, I think something might have popped up. Do we have time or?
I think we still have time. So if you have any questions, you maybe put it in the chat or. Okay. In that case, maybe if you have further questions, you can send emails to Chidinma afterwards. And thank you much for your presentation.
Thank you.
Right, so I would like to thank all 4 speakers and CIGRE B4 Study Committee for organizing today's event. And I would also like to thank Ying, Melike, and the event team in the CIGRE UK NGN. I would especially thank Charlotte for your help and support. And thank you very much, everyone, for joining today's event, and I hope you have enjoyed it. The CIGRE UK NGN and CIGRE B4 Study Committee will have a series of events to be held in the very near future. Please keep an eye on the CIGRE UK LinkedIn page or subscribe to our mailing list from the website. Looking forward to seeing you in our future event. Thank you.
Thank you.
Thank you, everyone.
Thank you.